Before we begin, a brief note for you. This analysis of the source material was structured and generated by an artificial intelligence framework. This helps us ensure comprehensive and, of course, impartial coverage of the technical content. Today, we're going to talk about a really significant paradigm shift, one that's reshaping software architecture as we speak. For a long time, AI has been, well, a mostly passive tool.
A predictive tool, yes. Models that could translate text or answer a very specific question.
Exactly. But now we're seeing a transition to a new class of system entirely. Autonomous AI agents. And it's important we define this precisely. An agent isn't just a model. It's a complete self-governing application.
One capable of genuine problem-solving and task execution. It merges that deep reasoning of language model with the practical ability to act on the world.
And that's the key. It can handle these complex, multi-step tasks without needing a person to guide it at every single stage. So our mission today is to formally guide you through the foundational concepts of these agents.
We'll cover their core anatomy, architectural design, and maybe most critically, the operational discipline you need to take them from a proof of concept to a robust production-grade system.
Let's start by deconstructing that core anatomy. When we look at these systems, we see four essential architectural elements that really have to be integrated for any kind of production-ready agent.
The first one is probably the most obvious.
The model.
The model, yes.
Yeah.
This is the brain, the core reasoning engine. It's the foundational language model that does all the planning. But the real insight here is that the agent itself becomes the ultimate curator of the input for that model.
It's managing its own context window.
Precisely. And that leads to the second element, the tools. These are the agent's hands, its interface with the real world. A model can only generate text, but tools like API extensions or vector databases let it take action.
So it can access real-time information or actually change something in an external system.
That's it. Then third, you have the orchestration layer. We can think of this as the nervous system. This is the process that governs the agent's main operational loop.
So it's handling things like planning, memory, and deciding which reasoning strategy to use, like a chain of thought approach.
Exactly. It's the architectural novelty here, what enables those complex sequential tasks. And finally, number 4 is deployment, the body and legs. This is how the agent is hosted on a secure, scalable server and integrated with production services.
Monitoring, logging, access control, everything you need to make it a reliable, enterprise-grade service.
And if you understand those 4 parts, the agent's operational process becomes much clearer. It's essentially a continuous loop between the model and its tools.
We can break that down into 5 distinct steps. The first is simply get the mission. This is the starting point. It could be a user request or some kind of automated trigger.
Once it has the mission, step 2 is to scan the scene. The orchestration layer gathers all the relevant context, is looking at its memory, checking which tools are available, and analyzing the user's specific request.
And after that scan comes the core of the process.
Step 3, think it through. Here, the reasoning model analyzes the mission and all that context to devise a multi-step plan. This is where it determines the sequence of actions it needs to take.
Once that plan is in place, it's time for step 4, which is take action. The orchestration layer executes the first concrete step from its plan, invoking whichever tool is appropriate.
Be it calling an API, running some code, or querying a database.
And that brings us to the final crucial step, which makes the whole thing a cycle. Observe and iterate.
Yes. The agent registers the outcome of its action. Was the data retrieved? Was there an error? It adds that new information to its working context, its memory.
And then the loop returns to step 3 to think it through again, but now with that new information.
And that think, act, observe cycle just continues until the mission is fully achieved.
Let's make this concrete with that customer support agent example. Let's say the agent gets a query. Where is my order? #12345.
Okay, so the orchestration layer immediately pushes the agent into the think it through phase. It reasons that to answer fully, it needs a plan. First, identify the order. Second, track its status. And third, report that information back.
That structure is important. It's not just guessing. So in the act phase, it starts with step 1. It calls the find order tool with the order number.
Then it observes the result.
Yeah.
Let's say that result includes the shipping carrier's tracking number. Now it has a new piece of information.
So the loop continues. It acts again, this time calling the get shipping status tool, using that new tracking number as the input.
Right. And it observes the carrier's response, maybe out for delivery. Only after it has successfully gathered all the necessary facts does it move to the final step, generating a clear factual response for the user.
That operational loop is clear, but how do you scope these projects architecturally? That brings us to a kind of taxonomy of these systems.
It's a way of classifying them by their capabilities, which is vital for scoping. We can start at the very bottom with level 0, the core reasoning system.
This is just the isolated language model. It's good at explaining concepts from its training data, but it's functionally, well, blind to the real world.
It can't answer what was the final score of the Yankees game last night, because that information is new and external.
But that limitation is overcome at level 1, the connected problem solver. Here, we give the reasoning engine access to tools.
Now it can interact with the world. To find that Yankees score, its think step would identify the need for external data. Its act step would then call a search API tool.
And its observe step would see the score, allowing it to synthesize a factual answer. That connection to the external environment is the first major leap.
It is. Then we move to level 2, the strategic problem solver. The architectural focus here shifts to planning for more complex multi-part goals. The key skill becomes what we call context engineering.
Meaning it's not just gathering facts anymore. It's actively selecting and packaging the most relevant information for each step of its plan. It's about intelligent filtering.
The coffee shop example from the source material is perfect here. The mission is, find a good coffee shop halfway between my location and my friends.
Okay, so the agent's first action is to call a maps tool to find the midpoint. Let's say that's Millbrae, California.
Now here's the strategic part. Instead of just doing a generic search for coffee shops in Millbrae, it refines its next action. It calls the Google Places tool, but it adds a filter, min rating 4.0.
Because the user specified a good shop, that autonomous refinement of the query based on the goal is the hallmark of level 2.
Exactly. And scaling up from there, we reach level 3, the collaborative multi-agent system. The paradigm shifts here from one super agent to a team of specialists.
So agents start treating other agents as tools. How is this different from, say, a traditional service-oriented architecture?
That's a key question. The difference is the generative nature of the delegation. A traditional system follows a predefined script. A multi-agent system gives a high-level goal to a specialized agent, and that agent autonomously generates and executes its own subplan.
The project manager agent is a great illustration of this. Given a mission like launch our new Solaris headphones, its main job is to break that down.
Right. It delegates subtasks to other agents. You might ask a market research agent to analyze competitor pricing, or a marketing agent to draft a press release.
Or a web dev agent to generate the product page, HTML. It manages the entire complex workflow.
And that brings us to the frontier, which is still mostly research. Level 4, the self-evolving system. This is where the system can perform what we call autonomous creation.
So it identifies a gap in its own capabilities and then builds a new tool for itself.
It invokes an agent creator tool to build a new specialized agent on the fly. If that project manager agent needed to track social media sentiment but didn't have the tool, it would just build a sentiment analysis agent and add it to the team.
That's a huge leap. Now, let's shift to the practicalities of building these systems. Model selection is a critical first step.
And it's where many teams make an error. They just pick the model with the highest academic benchmark score.
But in the real world, you have to define the business problem first. The best model is the one with the optimal balance of quality, speed, and cost for your specific task.
Which naturally leads to a strategy of model routing.
Mm.
A robust architecture shouldn't use one model for everything. You might use a powerful one, like a Gemini 2.5 Pro, for the complex initial planning.
But then route simpler, high-volume tasks like data extraction to a much faster and cheaper model, like Gemini 2.5 Flash. It's essential for managing performance and cost at scale.
Now for tool implementation, we can organize the tools into two main categories. The first is for retrieving information.
This is all about grounding the agent, in fact, to prevent hallucinations. So this includes things like retrieval augmented generation, vector databases, and tools to query SQL databases.
The agent has to be designed to look things up before it speaks. The second category is for executing actions, enacting real-world changes.
This is where you wrap existing APIs for tasks like scheduling a meeting or updating a customer record in a CRM.
Crucially, this category also has to include human-in-the-loop, or HITL, tools. These are tools designed to pause the agent at a critical point and ask a person for confirmation before proceeding.
For high-risk actions.
Exactly. And for any of these tools to work reliably, you need standards. Things like the OpenAPI specification, which provides a clear contract for what the tool expects and what it returns.
This whole shift from deterministic software to these stochastic reasoning systems demands a new operational philosophy, and that's agent ops.
It's a discipline that adapts best practices from DevOps and MLOps for the unique challenges of agents. The first discipline here is measurement. Success is no longer just, did the code run?
You have to measure real business impact, things like goal completion rates, accuracy, and the cost per interaction. It needs to be treated like a continuous A/B experiment.
And since simple pass-fail testing doesn't work, for quality evaluation, you use what's called an LM judge. This is another powerful language model that assesses the agent's output against a predefined rubric.
So it checks for things like factual grounding or adherence to a specific persona, all against a trusted golden data set of test cases.
Then there's debugging. When an agent does something unexpected, you need to know why. The answer is OpenTelemetry traces.
A trace is a step-by-step recording of the agent's entire thought process.
Its internal monologue, it shows you the prompt, the reasoning steps, the tool it chose, the parameters that generated, everything. Without that forensic detail, diagnosis is nearly impossible.
And finally, there's human feedback.
The most valuable resource you have. When a user corrects an agent, they're giving you a high-value edge case you missed. The agent ops process has to close the loop.
You capture that specific scenario and turn it into a new permanent test case in your evaluation dataset.
Which ensures the system is always learning from its real-world mistakes.
This brings us to a major concern: security and governance. The autonomy of these agents really complicates things. For a single agent, you have this inherent trust trade-off.
The more power you give it for utility, the more risk you introduce. So security has to be a defense-in-depth approach. You need traditional, deterministic guardrails, hard-coded rules like never approve a purchase over $100.
But you also need reasoning-based defenses. So using smaller, specialized AI models to screen the agent's plan for any rogue actions before it gets executed.
And architecturally, we have to recognize agent identity as a new class of security principle. An agent needs a verifiable digital passport separate from the user who kicked it off or the server it runs on.
This identity allows you to enforce the principle of least privilege. You can write policies that constrain access. The sales agent can access the CRM, but it's blocked from the financial systems.
Which contains the blast radius if something goes wrong.
Yeah.
But when you scale this up to a whole fleet of agents, you face what's called agent sprawl.
The uncontrolled proliferation of agents. The solution here is a control plane, a central gateway that all agent traffic must pass through.
User to agent, agent to agent, agent to tool, everything. This gateway becomes your central point for enforcing authentication and authorization policies. It turns chaos into a manageable, auditable ecosystem.
Let's talk about how these agents interoperate. Agent-human interaction is moving far beyond simple text chat.
We're seeing live mode with bidirectional streaming of audio and video, and even a tool category called computer use, where the model can literally take control of a UI, clicking buttons, filling out forms, with human oversight, of course.
And for agent-to-agent or A2A collaboration, there are two key standards. First is discovery, which relies on an agent card. It's a JSON file that basically advertises what an agent can do.
Then for communication, there's a task-oriented protocol that allows for long-running asynchronous jobs. It's essential for those level 3 multi-agent teams to work together effectively.
Interoperability is even extending into finance with agents and money.
Yes, new protocols are emerging. The Agent Payments Protocol, or AP2, uses cryptographically signed mandates to give agents delegated financial authority in a secure and auditable way.
And then there's a BY 402 standard for machine-to-machine micropayments.
It allows agents to operate in a fully automated economy, paying for API calls or digital content on a true pay-per-use basis without needing pre-authorized accounts everywhere.
So how do these agents evolve? How do they learn?
They learn from runtime experience, those traces and human feedback loops, and from external signals like new company policies. This learning results in the generation of reusable artifacts.
For example, a learning agent might observe a human expert correcting compliance reports. It can then autonomously update the guidelines that a separate critiquing agent uses, directly embedding that human expertise into its logic.
For more advanced offline learning, you have the concept of a simulation and agent gym. This is a dedicated off-production platform, a safe digital crash test environment.
So you can use synthetic data and red teaming to pressure test an agent and guide it through trial and error without ever putting live business data at risk.
Exactly. It's crucial for hardening agents against unforeseen edge cases.
And we are already seeing some incredible applications of these complex systems. Take the Google Co-Scientist project. It's designed to function as a virtual research collaborator.
It uses a high-level supervisor agent that delegates tasks to an ecosystem of specialized agents to systematically generate and evaluate scientific hypotheses, really accelerating the pace of discovery.
Then there's the AlphaVolve agent, which discovers and optimizes new algorithms.
It combines the code generation of language models with an automated evolutionary evaluation system. It has already found faster algorithms for things like matrix multiplication, and importantly, it outputs human-readable code.
So to summarize our analysis today, it seems clear that autonomous generative AI agents represent a pivotal evolution. We're moving from AI as a passive tool to an active, autonomous partner.
And success in this new world really hinges on architectural rigor. It's not just about the power of the model. It's about robust tools, sophisticated context management, comprehensive evaluation through agent ops, and secure governance.
The transition is fundamentally about managing complexity and leveraging that autonomy safely.
It is. For anyone looking to go deeper, we highly recommend exploring the comprehensive source material for more on these foundational concepts. We also encourage all friends of the show to subscribe for more technical analysis of this field as it continues to evolve. We wish you a productive and insightful day.